David Smith here with another flipped classroom math video. A few tips before we get started. Remember, you can always pause the video if you need to catch up with your notes. You can also speed up or slow down the playback if that helps. Finally, you can turn on the captions so you can see my words going by at the bottom of your screen. David Smith here with one more video on using differential calculus with an optimization problem. Now, this is a manufacturing problem, and typically manufacturing problems have a function that gives us revenue, how much money we make per unit or per item sold, that's our revenue, and then how much it costs to make the items. And we're always interested in profit with businesses. Mostly it's always a profit-based question. So what we want to do is we want to maximize profit. In manufacturing, there's always an optimum output to maximize the profit, which indeed, that's what this problem is all about. So let's jump in there. So Salt Creek Fishing Company makes fishing poles. Okay, sounds good. Here's the cost to make the pole. So we have an equation for that. It's 7x plus 3, cost as a function of x. Now in this problem, x is a batch of 1,000 poles. So it's not just one pole, it's 1,000 poles. So maybe the costs are relatively minor per pole, so they choose to do this per batch of 1,000 poles. So this x stands for 1,000 poles, okay? So if we made 2,000 poles or 5,000 poles, this function would tell us how much that would cost for us to make those poles. Okay, now revenue, not profit. Revenue is kind of like gross sales. It's like how much do we take in from selling the poles before we subtract out the cost. So revenue from the poles is this function. And you're just being given this. This is not one that you should have figured out. And the revenue function is the cube of the number of batches minus 10 times the batches squared plus 20 times the number of batches. So a cubic function is going to give us our revenue in this fishing pole making company. Okay, so a couple other things. The company right now can only make 1,200 poles. Now, the problem that I got out of the book doesn't specify any kind of time frame. So we could say this is 1,200 poles per week or 1,200 poles per month. If it's a big company, it should be per week. I would think they make that many poles per week. But really, we're not dealing with a unit time in this problem, but there should be one. Okay, first question. What is the domain of x? What can x be in this problem? There's a little bit of a critical thinking step in here because x here is a batch of 1,000 poles. So you have to use that and a little bit more of the information to come up with the domain. So pause the video, think about that, and write down your best thought as to what the domain is. Okay, so here's my domain. The key to realize is that if we can make 1,200 poles is our max, that's going to be 1.2 batches of 1,000 poles. So this time we have x, you could make no poles, so it's greater, x is greater than or equal to 0, but less than or equal to 1.2 batches. So that's our domain. So as we chunk through the algebra and the differential calculus of this problem, we need to remember that when we get some solutions, when we find some x's, we need to remember that we really only want something between 0 and 1.2. Okay, I cleaned up that board to give us more space, but I summarized the important findings from that last board. Here is the cost function per batch. Here's the revenue function per batch. And then here's our domain. We could have 0 up to 1.2 batches in our function, in our factory. Okay, so here's your prompt. Write an expression to calculate profit. And I'm going to get you started. I'm going to say P of X for profit is going to equal something. So pause the video and see if you can figure out what goes there. Very simple. We're not putting a lot of algebra in there yet. Here's your prompt. How many poles should be made to maximize the profit? So I want to give you the broad steps, but I'd love for you to pause the video and try your hand at the algebra, taking the derivatives, and see how far you can get. So Here's what we want to maximize, P of X. We have expressions for R of X and C of X, revenue and cost. So take these expressions, combine them together like it shows here with the minus sign, get one polynomial, combine your like terms, take your first derivative, analyze, second derivative, analyze. You've been through these steps a couple times already, so see how far you can go. I will come back and walk you through it step by step. Okay, here's what I get. I did my plug-in step here. I just put in my revenue function and subtracted my cost function there. Kept my parentheses around because this minus not only applies to this, but it also applies to the 3. So then I just combined my like terms. I subtracted my 7x from my 20x, gave me 13x, and then I brought down my minus 3. Now I know I'm going to need to take the first derivative and set it equal to 0 and do all that. So I went ahead and took my first derivative of my profit function, and I get 3x squared minus 20x plus 13. Now, this one is a little bit harder to solve on paper. So what I'm going to recommend you do is pull out the calculator and use the polyroots or whatever function you have on your calculator to solve for x for this. So set equal to 0 and solve for x. Okay, so my calculator gives me two values here. It gives me x equals 0.730. Okay, cool. And it gives me also x equals 5.94. Now, I can throw one of these away. My domain has to be between 0 and 1.2 because I could only make 1,200 polls or 1.2 batches. So this value is not good for this problem. So this one would be my solution, which is 0.73 batches or 730 polls. That's what would maximize my profit. But let's do some checking with our second derivative. So pause the video and take the second derivative. Okay, so I brought the previous stuff up from below. Here's my the first derivative of my profit function and my two solutions for that. And then here's the second derivative, just taking it of the first derivative. We've got that. Now, we're assuming that this 0.730 is a maximum. But we're assuming that. Makes sense, but we don't know. So if we're not graphing the profit function, we're just doing this on paper, we need to check. We need to make sure that that's a maximum before we go to the production manager and say, yep, crank it up, we're gonna make 730 polls, okay? You wanna be doubly sure. So what we do is we do the second derivative of 0.730 and we check to see whether that's positive or negative. So go ahead and pause the video, figure out what that is. Okay, so I went ahead and did this. This is my turning point, right? But we just don't know if it's a max or a min. So I did my my second derivative of 0.730, did my plug-in step. I wind up with minus 15.6. So that's a negative number. Now, when the second derivative gives you a negative number, what does that tell you about the original function? Think about that for a minute and come back. Okay, what it means is that it's concave down. So concave down. So in a very rough sense, this point here is concave down. So that means it's a max. So that means it's good. We are at 0.730 batches, so we can make 730 polls, and that will maximize our profit. Here's a slightly different question. Hint, there's no differential calculus in this question. It's very answerable. Okay, so for what values of X does the company break even? Now, a little bit of context here. If I have my company sitting here and I've got my plant and I've got my workers all standing there and all ready to go, and I don't make any fishing poles, I'm losing money. I'm paying rent, I'm paying interest on loans I took out to buy the equipment, and I'm paying my employees. But I'm not making any fishing poles at all. So I'm taking a loss when I'm not making poles. So as I start to make more and more and more poles, my revenue is going to increase until finally at a certain level of production, my revenue is going to equal my cost. And that's good, that's break even, but really I'm here to make money. So I want to make even more poles so that I'm having a profit. So that's when the revenue function is bigger than the cost function. So you've got these two functions. You've got your cost and your revenue. So see if you can do some algebra and find out where you break even. What's the number of, in this case, batches allow us to break even? Companies want to know that because then they have a target. They know, okay, we're going to start up our company. We need to be making at least 200 poles a day or a week to break even. And then they know what that target is so they can watch their process and make adjustments and pay attention when it's necessary. So pause the video and see if you can do the algebra necessary to find those places. In case you were stumped, here is a big prompt. The break-even point happens when the cost equals the revenue. Now you have those functions back there. So put them in place here, get them all on one side, combine like terms, set equal to 0, and solve for x. Okay, so here's my plug-in step. I just put my cost function in here, I put my revenue function there, then I moved my cost function over to this side by subtracting it. So really that only just decreased my 20x term to 13x and slapped a -3 onto the end. Now this is a cubic function. Get out your calculator to solve that. There's more than just two solutions, but the two solutions we're interested in are the ones that fall within our domain of 0 to 1.2 batches. So we had 0.296 and we had 1.19. So that's just below our 1.2 batches. So the break-even points, because there's two, we're going to take a look at why that is in just a sec. We break even once we ramp up to 296. But remember, our maximization point was 730 poles. So as we make more poles, we're actually making less profit, to the point where if we make 1190 poles, we're back at our break even. So to finish this little piece up, think about what the graph might look like. Or get out your calculator and put these two functions in the calculator and look at what they show you about what's happening. Okay, I went ahead and graphed my cost function and my revenue function to illustrate that these are break-even points. So check this out on the graph. The cost function, 7x plus 3, that's a linear function. It's a line with a slope of 7 and a y-intercept of 3. So I just drew that right there, 7 or 3, and I'm making this have a slope of 7. Okay? So that's my cost function. Now, my revenue function is a cubic function, and I'm only drawing it in the range that we are concerned about. Actually, I'm drawing a little bit further beyond that range, but really, we're not going to have negative revenue. Well, yeah, we're not going to have negative revenue. So I just drew it where the thing is positive. This is a cubic function, so it's going to do a double loop. It's going to go down and back up again. But this is the part that we are most interested in. And you'll see here at 0.296, that's where the revenue and the cost meet. So that's a break-even point. And as we make more poles, our revenue is higher than our cost. So all the way to here, to 1.19, we are actually having profit. This area there, that area, if I shaded that, that would be the profit. And if this is an econ class, we could do that kind of thing. And we do a lot of graphs in econ that show these things. So this area here is our profit. Now, as you make more poles, suddenly my cost continues to increase, but my revenue is dropping off. So I'm having fewer and fewer. I'm actually not breaking even anymore. My revenue is less than my cost, so I'm running at a loss. So as a manufacturer, I'm going to make between 296 and 1190 poles. Not going to make any more or less because I'm losing money if I do that. Okay, so just for grin, since we are doing a lot of graphing in this last couple lessons, I'd like you to throw on the profit graph, and you can take your cues from this graph, just like we do when we're sketching derivatives based on function. Okay, so check this out. my profit is only positive. We only have a profit from the point where our revenue is greater than our cost. So it's only between the two break-even points. So my profit is this little blip right there with a maximum at 0.730 units or batches or 730 poles. That's the maximum profit. And then the interesting thing is that if we go zipping up the graph like right up there, if I drew it correctly, this point, 0.730, that's the longest segment, the longest vertical line between the revenue and the cost curve. And I think my graph isn't quite accurate enough to show that well, but you can see the idea is that the farther the revenue curve is above the cost curve, the bigger the profit. And so that biggest part of the bulge there is going to coincide with the max of our profit function. So pretty cool stuff, I think. Now that you've watched the video, take a moment and write down any questions that you might have so you can bring them to our next class. Remember that you can always watch the video again and perfect your notes. Finally, if you enjoyed the video, please click the like button down below. And if you'd like to help me grow my YouTube channel, please click subscribe.